Okay, so we came up with something called electric flux, but we don't know what is flux and how do you calculate it. So today we cover that. Electric flux can look intimidating because it mathematically involves something called a surface integral, which is more or less what it sounds like, the summing up of contributions from a function all across the points on a surface. Surface integrals can be pretty nasty, but ours generally won't be because we'll use symmetry to defang them. So you hopefully run into integration, and the idea of integration being adding up contributions. In other words, the idea being we have some graph, and we and we have some function, and we say in some little region I make little triangles or rectangles or whatever, and I add up theirs so as to give me the area of underneath that function in one dimension. And we might say like some other function g is the integral of f dx. Now we're going to talk about having things like maybe a cylinder, and we'll have some thing coming out of the cylinder at all different angles, and we'll be computing something which is an integral of that function over the area of, say, our cylinder or whatever. And don't worry if this looks a little intimidating right now. It's actually relatively straightforward, and what we'll need to do with it will be even more straightforward than that. We're going to start off by working with an analogy that's a little easier to visualize. Imagine you have a wire loop placed near a box fan. So you've got a fan in the window, and someone has taken a wire, a little square of wire, and they've attached little streamers, little pieces of metal, little pieces of paper that hang there, and in the wind they show you the direction the air flows. All right, as the air blows by, it will stream out the streamers, why they're called streamers, and tell you what direction the air is flowing, because the streamers will point in that direction. And then we can imagine for a given airflow, if we orient that loop in different ways, the streamers will point along the airflow and it will look a little differently. We get maximal airflow through the loop if the angle sort of between the streamers and the velocity is 0. And we would get no airflow through the loop if the angle between the streamers and the velocity were 90. And in between we get some difference where we get airflow, which is sort of v cosine theta, which tells us how much of the air is perpendicular to the loop. All right, we get most effect. If you imagine having a steady stream of air, we get the most effect if the loop is perpendicular to that flow of air, and we get almost no effect if it's parallel. So now we're going to find a vector which we call the unit normal, which is of length 1 and points perpendicular to the plane of the loop, symbolized by this symbol, which is called n hat. Just like we had I hat and j hat and k hat, or x hat, y hat, and z hat earlier, where they were unit vectors in the x, y, and z directions. This is a unit vector that just points in some direction, and we're going to denote it by n hat. Remember, it's a unit vector. It doesn't have any units to it. It has no dimensions. It's just the number 1 pointing in a given direction. Then we can define our angle theta to be between the velocity air and the normal of the loop. So the idea being, if this is my loop, the normal to the loop points perpendicular to the plane that contains the loop. Wow, that was pretty bad. Let me redraw that. So if we have this is our wire loop, then the direction perpendicular to that loop is the normal vector. And then we see that only the perpendicular part of the velocity carries any air through the loop. In fact, the volume of air that comes through the loop will be something like the velocity perpendicular to the loop times the area of the loop, because during that time we sweep out sort of this volume. Oops. And notice that this agrees with our intuition for aligned cases where theta equals 90, and therefore we get maximum volume of air through. And when it's a thwart, when theta equals 0, and we get no airflow through the loop. We're going to define the electric flux analogously. We're going to say that the electric flux, symbolized by the Greek letter phi for flux, and usually this little subletter E just to say that's the flux of the electric field. You'll see that come and go as people are lazy or not in writing it, but in principle we should say the electric flux through a surface is the electric field strength times the area times the cosine of the angle between them. All right, so down here we have a little picture of it, and we say that E perpendicular, if you want, is E cosine theta is the part of the electric field that passes through the surface. Some of the electric field is sort of sliding along the surface, and some is coming out, coming through. You'll hear us say a lot, piercing the surface. It's probably important to say we're going to use terminology based on fluid flow a lot here because that's how we visualize it. It's easy to see. But the electric field is not actually a flow, and there's no there's nothing spewing across this thing. We're just saying how much of the vector seems to point through as if it were a fluid flow. That's kind of annoying to get used to it. Our expression looks a lot like a dot product. You know, something times something else times the cosine of the angle. And so we define this weird but interesting thing, the vector area of a surface. We don't usually think of that. We usually think of areas as just numbers, as scalars. Now we're going to say that the vector area of a surface is a vector which points along the normal and has a magnitude equal to the area of the surface. So, kind of goofy, but oops. We'll define dA is the little bit of area in the normal direction. So we do this, and if we had like a rectangular loop of length and width, and then we said that this was the direction normal to it, then we would have length times width times that normal, and so on. It's the first time we've really done that, but it's kind of interesting. You might say, well, which way does it point? Because for that little square block there is a normal that points outward and a normal sort of points the other way, and they're both perpendicular. And for open surfaces like a plane, that's actually kind of a mess. But for closed surfaces, we'll have an easy definition. This allows us to come back and have a definition of the electric flux as just E dot A. That's the flux through the surface A. And this would allow us to deploy all of our vector knowledge as well. A couple of caveats on the definition, but we'll handle them later. 1, the surface here is planar, so there's only one normal vector. And 2, the electric field does not vary at different points on the surface. And we'll want to be very careful about that. If the electric field were in different places, we haven't really defined that if it weren't constant. And we'll have to come back and do that. Some illustrations of area vectors and of how they interact with flux. Nothing particularly big. Square loop, the area vector points just simply out, and it's easy. Compute it L times L, W. Circular thing still points perpendicular, has the area that you'd get like pi r squared. You might see that these are essentially saying do a right-hand rule, curl around counterclockwise around these things, and you get the right-hand rule. But don't worry about that because we don't need that much. And then we say the electric flux is how much of the electric field is threading through that area, and we would take the component, either the perpendicular part of the electric field, because if we look at any one of these electric field lines, there's a part that's coming out and a part that's sort of sliding along the surface. And the stuff that's sliding along the surface doesn't contribute. It's not going through the surface. Just like if this were a fluid flow, stuff sliding along here doesn't contribute to volume of fluid passing through. So we use E cos theta, and that gives us the dot product bit. All right, but what if the electric field is not constant throughout the surface? Well, then we deploy our usual trick of mentally subdividing the surface into many, many, many smaller regions, each of them so small that we consider the electric field to be constant throughout any given one of them. Of course, for a given tiny region, we'd have an infinitesimal area, amount of area, so we'd have a correspondingly infinitesimal amount of flux. So in this case, we would write this as d phi sub E. The infinitesimal amount of little flux is the electric field through some area dotted into the infinitesimal tiny little area. So if we have, I'm going to try and come up with a decent picture here. If we have a, say, cylindrical place, and we're only worried about right now the cylinder, like so we've opened paper tube or something, then we would subdivide this into many, many, many regions, with the idea that the region is such that although the electric field might be different for different places, that for each of these little squares, the electric field is constant. So even though it might vary tremendously over the surface of the cylinder, we will subdivide the cylinder into little regions so small that for that little region, we don't get very much change in the electric field. If we can do that, then the total flux is just the sum of all the tiny fluxes, or the electric flux in total is the sum of all the infinitesimal electric fluxes, which is the sum of E dot dA. An aside, a result that we're going to use a fair bit is somewhat obviously, if we add up all just the areas, we integrate just dA, we should get the area of the surface. Right? If we break the surface into little pieces and then we add up the area of all those little pieces, we should get back to having just the area of our surface. Also, and this is useful to know, while the expression is true for any surface, the flux through any surface is the integral of E dot dA on that surface, it ends up it's only useful for closed surfaces, surfaces that have definite insides and outsides. We'll see in a little bit why that's the case. Because of that, there's a notation that's used in math to indicate that the integral needs to be over an entire closed surface. We put this little loop here, which is meant to be a closed circle or a closed surface. And you'll see that notation a lot in math back and forth. Often people are a little sloppy, but you shouldn't be. If your result depends on it being closed, you should indicate that it is closed. For our integral, we always take the outward bound normal, the outward pointing normal. What does that mean? Well, of course, with the plane, remember, we said there were two possible, right? If I have a particular plane, there really are two directions normal to it. There's, maybe this one, which is at right angles, but there's also, if you imagine that one at right angles, and those are both normal to the plane. So you'd have to decide which one you want, which is tricky and annoying. But for a closed surface, it's nice and simple. When we have any closed surface, there's an inside and an outside. That's what makes it closed. And we will always just take the one that points outward. Wherever we are, the thing normal to a tangent plane that points out of the surface. This is one of the cases where we could have chosen the other. It would just flip the sign for everything, and we don't do it that way. All right, consider a radially symmetric electric field, one whose strength depends only on distance from some point. That is to say, the electric field as a vector, E, is the electric field as a function of R times the radially outward bound normal. And we're going to construct a Gaussian surface, which is a sphere of radius R. That makes sense. So we've got some electric field radiating out from some point. We're going to sketch out some imaginary sphere. And I'm going to say the area of element, the element of area would have a normal vector pointing radially outward, because that's what's normal to a sphere. Right? So dA would be the area times the r hat vector. And so the element of flux, d phi, would be E dot dA, which is E r hat dot dA r hat. Can group the scalars up, it's EDA. And then I have r hat, but any unit vector dotted into itself is 1. Right? The unit vector is, of course, fully aligned with itself. Also, just as a side, notice that I told you sometimes I'm lazy, this really should have a little subscript E. I don't think it's that important, but you'll see it a lot, so I wanted to point it out. All right, here's the magic. We'll want to integrate all of the little d phi's, but we'll integrate on the surface of the ear where the radius is constant, and the electric field is a function of the radius. So the electric field is also constant on the surface of that Gaussian sphere. That means that we can take E outside of the integral sign. Right? Phi is the integral of d phi, which is the integral over a complete surface of E dot dA, which is the integral over a closed surface of EDA, but E is a constant, so it comes outside. So now we have the integral over the closed surface of A, of dA, which is, as we said before, the integral of dA is just A, so we have that phi is just the electric field times the area. And we know the area of a sphere is 4 pi r squared. So the electric flux is the electric field times 4 pi r squared. Notice how much easier that was because we chose a Gaussian surface that matched the symmetry of the electric field. That's why we talked a lot about symmetry before, and why we're going to continue to exploit it as much as we can throughout this section. And hey, what do you know? We already know a charge configuration that produces an electric field that is radially symmetric. That is a single point charge Q. Right? We know that the field around a point charge, right? If I have a point charge Q, the electric field points radially outward. And we know its field actually. We know the field would be 1 over 4 pi epsilon Q over r squared. So we can actually just compute the flux directly because we can take this and multiply it by the area. E times A. And notice that what ends up happening, the r squares cancel, the 4 pi cancel, and we just get Q over epsilon naught. You might have wondered, that's why we defined epsilon naught way back when. We wanted to get rid of that factor of 4 pi. You're going to see that it's inconvenient in anything but the Coulomb law, and this is the first case where it goes away. We get that the electric flux is just Q over epsilon naught. This result will actually hold for any surface we had drawn around a point charge, even though we derived it for a sphere. Your textbook has a nice run-through that's a quasi-proof as to why, and it's worth reading. What if we had drawn a Gaussian surface that doesn't enclose the charge? So here is our charge, and we draw this Gaussian surface, which is kind of dumb, but we draw that one. Then it can be shown, which is pretty easy, and your textbook does a really nice job of it, that the total flux would have to be 0. There's as much flux coming in as going out, and therefore every bit of field that pierces here, as this field is drawn, here's the field, and every bit that pierces, it goes in here, but then it leaves later, and goes in, but then it leaves. And there's a somewhat better proof that shows that that has to be the case. What if there had been multiple charges? Well, we can use the superposition property. We can say that the flux of the electric field, total electric field, right? The electric flux total is the flux of the total field, but the total field is the sum of all individual fields. So we get a whole bunch of E.da's just for each individual field, and each of those are their individual fluxes, which turns out to be Q1 over epsilon plus Q2 epsilon, etc., or just Q total over epsilon naught. But any collection of charges, even continuous charges, can be considered to be made of point charges. So this holds for any charge distribution. And we are finally and at last at the important bit. This is Gauss's law, that the electric flux through a surface is exactly equal to the enclosed charge over some constant, that the flux is proportional to charge. The flux through a Gaussian surface is directly proportional to charge contained with that surface. And this kind of makes sense, or should make some sort of sense, because it ends up saying the electric flux is measuring how much field you have, and the field is generated by the charges. The more charges you have, the more fields coming out, the more flux you would expect coming through any given surface. This whole thing is called Gauss's law. It's one of the 4 fundamental laws of electrodynamics, and we'll talk a little bit later in class of a different form of it. This is essentially an integral form because, of course, this is implicitly an integral. That integral of E dot dA over a closed surface is proportional to the charge inside that surface. Important here, only the stuff inside the surface, which is going to be kind of interesting. All right, so here we're given that the electric field is constant over each face of the box. Does the box contain positive charge, negative charge, no net charge, or not enough information to tell? Well, we can see that exiting the box, we have 10 plus another 20 plus another 15. So that is 45 exiting the box. And entering the box, we have 15 plus 15 plus 20. And that's 50. So there's more field lines entering the box than exiting the box, which means some of them must disappear inside the box, which means there must be negative charge to act as the sink for that field. Which Gaussian surface has the larger electric flux? Surface A, surface B, they have the same or not enough information. So we end up with the amount of flux through the surface is just equal to the charge inside. And clearly case B has more charge inside and therefore has more flux through the surface. Kind of interestingly, if they had reversed the case, if there had been if there had been a case of here are our Gaussian surfaces, and here is 2q, and here is only 1q, then this would have had more flux, even though it's much smaller in terms of area. All right. Spherical Gaussian surfaces of equal radius r surround two spheres of equal charge q. Which Gaussian surface has the larger electric field on it? Well, they have the same amount of charge at the inside. And again, we have E dot dA integrated is the enclosed charge over epsilon. This is the same. And this is the same. So the electric fields must be the same. The electric flux is shown through two different Gaussian surfaces. In terms of charge Q, what are charges Q1 and Q2, where this off-color kind of tan surface has a flux which is 2Q over epsilon naught, and this grayer surface has a flux which is just 1Q over epsilon naught. And we know that the flux through the surface is equal to the charge enclosed over epsilon naught. So for this first one, it says that there's 2Q inside. But the only thing inside this surface is Q1. So we see immediately that Q1 is 2Q. On the other hand, the charge inside this surface is Q, and it's made of both Q1 and Q2. So Q is 2Q plus Q2, or Q2 is minus Q. So we're at this one.